The essential information of a linear system can be recorded compactly in a rectangular array called a matrix. Therefore, our ability to analyze and solve systems of equations will be greatly enhanced after we learn how to perform algebraic operations with matrices. Hello everyone, my name is Rafael. I am an electrical engineer, and in this video I would like to share with you my views on matrices, determinants, and linear systems. Let's begin with simple matrix operations. Addition and scalar multiplication. If A and B are m by n matrices, the sum of A and B will be a matrix which has the same number of rows and columns of A and B, and is computed by adding the corresponding elements of A and B. If R is a scalar and A is a matrix, the scalar multiplication RA is the matrix whose elements are R times the corresponding elements of A. Let's see an example now. Let A and B be this matrix here. A is this and B is this. We want to calculate A plus B, 2 times B, and A minus 2B. Okay, my friends, this is the first example. Let's compute first matrix A plus B. Let's call C equal to A plus B. The elements of C will be obtained by summing the corresponding elements of A and B. Four plus 1 is 5. The first element of matrix C resulting from the sum of A and B is 5. Now the second element, or if you prefer, the second entry, 0 plus 1 is simply 1. 5 plus 1 is 6. How about here now? Negative 1 plus 3 is positive 2. 3 plus 5 is 8. And 2 plus 7 is 9. It's very simple. We simply sum the corresponding entries of A and B. This entry here is A11. This entry here is B11. We sum A11 with B11 and we get C11 and so on. This is how we add matrices. Now let's compute 2 times B. Let's call it matrix D. D is equal to 2 times B. How do we do it? We simply multiply every entry, or if you prefer, every element of B by 2. 2 times 1 is 2. 2 times 1 is 2. 2 times 1 is 2. 2 times 3 is 6. 2 times 5 is 10. 2 times 7 is 14. This is how we perform scalar multiplication with matrices. The next step is to compute A minus 2B. Let's call it E. E is equal to A minus 2B. We have A is this, 405, negative 1, 3, and 2, minus 2 times B. We already have 2 times B here, minus 2, 2, 2, 6, 10, and 14. It is very simple. We simply subtract the corresponding entries or elements of each matrix. 4 minus 2 is 2. 0 minus 2 is negative 2. 5 minus 2 is 3. Negative 1 minus positive 6 is negative 7. 3 minus 10 is negative 7 too. 2 minus 14, negative 12. Okay, my friends, this is very simple. Performing matrix addition or subtraction and multiplying by a scalar. Okay, now we are going to move on to matrix multiplication. We are going to learn how to multiply two matrices. Matrix multiplication. If A is an m by n matrix and B is an m by p matrix, matrix C resulting from the multiplication between A and B will be an m by p matrix. Matrices can be multiplied only if the number of columns of the first matrix is equal to the number of rows of the second matrix. Otherwise, they cannot be multiplied. Let's see an example. Let's calculate matrix C resulting from the multiplication of A and B. Matrix A is a 2 by 2 matrix. Can you see that A has 2 rows and 2 columns? Multiplying matrix B, which is a 2 by 3 matrix, can you see that matrix B has 2 rows and 3 columns? As the number of columns of the first matrix is equal to the number of rows of the second matrix, they can be multiplied in this order, and the matrix C will be a 2 by 3 matrix. C will be a 2 by 3 matrix. Okay? If matrix A is this matrix and the matrix B is this matrix, matrix C will be, as we saw, a 2 by 3 matrix, having entries C11, C12, C13, C21, C22, C23, okay? Let's calculate then. C11 is going to be obtained from the multiplication of the first row of matrix A with the first column of matrix B. Therefore, C11 will be 2 times 4 plus 3 times 1, and this is equal to 11. Similarly, entry C12 will be obtained from the multiplication of row 1 of the first matrix and the column 2 of the second matrix. And then it is going to be 2 times 3 plus 3 times negative 2. And this will be equal to 0. Continuing, entry C13 is going to be obtained from the multiplication of row 1 of the first matrix and column 3 of the second matrix. It is going to therefore be 2 times 6 plus 3 times 3, and this is equal to 21. Now, entry C21. Entry C21 is going to be obtained from the multiplication of row 2 of the first matrix and column 1 of the second matrix. It is going to be 1 times 4 plus negative 5 times 1. And this is equal to negative 1. Likewise, entry C22 is going to be obtained from the multiplication of row 2 of the first matrix and column 2 of the second matrix. C22 will be equal to 1 times 3 plus negative 5 times negative 2. And this is equal to 13. Finally, entry C23 is going to be obtained from the multiplication of row of the first matrix and column 3 of the second matrix. Entry C23 is going to be 1 times 6 plus negative 5 times 3. And this is equal to negative 9. Okay, my friends, this is how matrix multiplication is carried out. Now let's see the transpose of a matrix. Given an m by n matrix, the transpose of A is an n by m matrix denoted by A to T, whose columns are formed by the corresponding rows of A. Let's see an example. Let A be this matrix. We want to compute the corresponding transpose. How do we do it? Take entry A11 in the transpose it continues being A11. But how about A12? A12 becomes A21. And A21. A21 becomes A12. A22 continues being A22. A31 becomes A13. And A32 becomes A23. Okay? In this manner, the transpose of A is -5, 1, and 0 to -3 and 4. Okay? This is how we convert one matrix into its transpose. Now let's see the inverse of a matrix. Let A be this matrix, A, B, C, D, and let B be this matrix here, B11, B12, B21, and B22. We want to assess whether one is the inverse of the other, and we want to express the entries of B in terms of the entries of A. Okay, in this way, A, B, C, and D multiplying B11, B12, B21, and B22 will produce another matrix, and this matrix will be the first entry of this matrix will result from the multiplication of the first row of the first matrix with the first column of the second matrix, and this is A times B11 plus B times B21. And now the second entry of this matrix will come from the multiplication of the first row of the first matrix and the second column of the second matrix. A times B12 plus B times B22. This entry here will come from the multiplication of the second row of the first matrix and the first column of the second matrix. It is going to be C B11 plus D B21, and the last entry of this matrix is going to come from the multiplication of the first row of the first matrix, the second row of the first matrix and the second column of the second matrix. C times B12 plus D times B22. Okay? And of course, if one is the inverse of the other, they have to produce the identity matrix. Okay? What we are going to do is to equal this to 1, equal this to 0, equal this to 0 and equal this to 1, and we find that B can be written in terms of the entries of A in such a manner: 1 over AD minus BC, D negative B, negative C, and A, and written in such a way, B is indeed, of course it is generic, we are using letters, not numbers, but this is indeed the inverse of this, okay? And what is this number here? You see that AD minus BC has to be different than 0, okay? We cannot have 0 here, alright? It is impossible. If we have 0 here, then A does not have an inverse. And this number here is precisely the determinant of matrix A, okay? The determinant of A is AD minus BC. And the result that we were looking for is this, the condition for invertibility. The determinant of a matrix has to be non-zero, otherwise the matrix is not invertible. Only matrices whose determinant are non-zero have inverse matrices, okay? This is the first result that we wanted to find related to matrix invertibility and the determinant of matrices. And the conclusion is a matrix is invertible only if its determinant is non-zero. Now let's see the techniques that are often used to find the inverse of a matrix, and let's apply these techniques on this matrix here. Example, find the inverse of matrix A. And how do we do it? To find the inverse of a matrix, we use the augmented matrix of the sort A with the identity matrix, and A with the identity matrix at the right side is the augmented matrix, okay? And we operate on the rows of the augmented matrix until the identity matrix appears at the left side. Let's do it. This is matrix A, and this is the identity matrix of the same order, order 3. We are going to operate on the rows of the augmented matrix until the identity matrix that is at the right side appears at the left side. This is a technique. What can we do first? Firstly, we swap rows 1 and 2. Okay? We swap rows 1 and 2. 1, 0, 3, 0, 1, 0, 0, 1, 2, 1, 0, 0. Negative 3, 8, 0, 0, 0. What did we do? We changed. We put row 2 in the place of row 1 and row 1 in the place of row 2. We can do it. Now we are going to use A11 as a pivot to put a 0 at A31. Okay? For this we operate as follows. -4 times R1 plus R3. Okay, we are going to multiply R1 by -4 and sum with row 3. And in this way, we eliminate this 4 here. It is going to be -4, 0, -12, 0, -4, and 0. 4, -3, 8, 0, 0, and 1. When we do this, when we multiply row 1 by -4 and sum with row 3, we find 0, -3, -4, 0, -4, and 1. Okay? And we put this in the place of row 3. In the place of row 3, we put the new row 3. It's 0, -3, -4, 0, -4, and 1. Okay, can you see the identity matrix appearing here? What we need to do now is to eliminate this -3 here. And we are going to use this entry, A22, as a pivot. Let's do it. Use the pivot A22 equal to 1 to place a 0 at A32, okay? And we are going to do this. We are going to multiply row 2 by 3. It becomes 0, 3, 6, 3, 0, and 0. And we sum with row 3, 0, -3, -4, 0, -4, and 1. When we do this, we find 0, 0, 2, 3, -4, and 1. And in the place of the old row 3, we put the new row 3. Zero, 0, 2, 3, -4, and 1. We are going to proceed in the same way, eliminating these 3 and these 2, and in the end we divide this by 1 because we want zeros on every entry, but the entries of the main diagonal, have to be 1. And in the end we find that 1, 0, 0, 0, 1, 0, 0, 0, 1, and the inverse matrix appears here, -9 halves, -2, 3 halves, 7, 4, -2, -3 halves, -1, and 1 half. Okay, and this is the inverse of matrix A. The inverse of matrix A is precisely this here. Negative 9 halves, negative 2, 3 halves, 7, 4, negative 2, negative 3 halves, negative 1, and 1 half. Okay, this is what we do. These are the steps that we have to take to get the inverse of a matrix. And this is all for matrices. Let's see the determinants now. For n greater than or equal to 2, the determinant of an n by n matrix can be calculated using this algorithm here. The determinant of A is the summation of I or j from 1 to n of Aij times Cij, where Cij is a cofactor associated to the element Aij. And Cij is calculated by negative 1 raised to the power of I plus j times the determinant of A minus I minus j. And what does it mean? It means that we are going to take the original matrix and remove the ith row and the jth column, okay? To compute the cofactor. This is called a cofactor. And this expression is accurate for matrices of any order, provided that they are greater than or equal to 2. However, for 2 by 2 and 3 by 3 matrices, other approaches are used. Let's see this example involving a 2 by 2 matrix. We have this equation. The determinant of this matrix is equal to negative 1. How do we compute the determinant of this matrix? 5x plus 15 minus 2x plus 1 is equal to negative 1. And if we carry out, we find that x is equal to negative 6. Alright? So this is a simple equation involving the determinant of a 2 by 2 matrix. Now let's use the rule of Sarri to calculate the determinant of a 3 by 3 matrix. The rule of Sarri, find the determinant of this matrix here, A equal to 2, 5, 1, 3, 2, 4, negative 1, 0, negative 3. Okay? To use the rule of Sarri, we rewrite the first and the second columns of matrix A and sum the products guided by the following arrows to calculate the determinant of A. We repeat the first and the second columns and follow the multiplication guided by these arrows here. The arrows of the left have to be multiplied by negative 1, and the products of the right keep the sign. Okay? This is the rule of Sarri as I understand it. You may have learned this in a different way, but it has to be similar. And then the determinant of matrix A will be equal to -1, okay, times 1 times 2 times -1 is -2. Here we have a 0, then it is 0. -3 times 3 is -9. 9 times 5 is 45. It is -45. Plus 2 times 2 is 4. Times -3 is -12. Plus, there is a 0 here, then it is 0. -1 times 5 is -5. Times 4, -20. And then we find, in the end, 15. This is the rule of Sarri. Now let's implement this algorithm here to calculate the determinant of a 4x4 matrix. We wish to calculate the determinant of matrix 2, 4, 1 and 0, 3, -2, -5 and 3, 0, 0, 1, 2, 3, 2, 1, -2 and 6. Okay? We are going to use the cofactor to calculate the determinant of this matrix here. The formula allows us to choose any row or column as our guide, but it is advisable to use the row or column with most zeros. As row 1 has 2 zeros here, we are going to use as our guide row 1. Then the determinant of matrix A is going to be A11 times cofactor 11 plus A12 times cofactor 12 plus A13 times cofactor 13 plus A14 times cofactor 14. However, look at A13 and A14. They are zeros, isn't it? So this multiplication here is 0, and this multiplication here is 0. We are left with only this here, okay? Then the determinant is going to be only this, because the other entries are 0. We know that A11 is 2 and A12 is 3. Okay? In this way, our determinant is going to be 2 times cofactor C11 plus 3 times cofactor C12. Okay? Very simple. Just use the algorithm. It requires a little bit of training, but it is possible. C11 will be equal, we are going to use this negative 1. I represents the row is 1. And J represents the column is 1 as well, times the determinant of the matrix, in which we remove row 1 and column 1. Okay, we are going to take the original matrix and remove row 1 and column 1, and the matrix that results from this removal is negative 2, negative 5, 3, 1, 2, negative 2, 3, 1, and 6. Okay? We remove the first row and we remove the first column, and this part only, this part here only, is what we are going to use here. And this, if you calculate in your house, this is equal to 17. We are going to do the same for cofactor C12. Cofactor C12 is going to be negative 1, row 1, column 2, and the determinant of A, which results from the removal of row 1 and column 2. We are going to go back to the original matrix and remove row 1 and column 2. For cofactor C11, we removed the first column. For cofactor C12, we remove the second column. And it becomes 4, 1, 0, 1, 2, negative 2, 3, 1, and 6. And this is equal to negative 44. In this way, we find that the determinant of A is equal to 2 times 17 plus 3 times negative 44, and this is equal to negative 98. Okay? And this is how we use the algorithm of the cofactor to calculate the determinant of matrices. Frequently, we use the rule of Sarri for 3 by 3 matrices, but for matrices of order greater than or equal to 4 by 4, we use this algorithm here to find the determinant. Now let's see some properties of determinants. Property number 1, row operations. Letter A. If a multiple of one row of A is added to another row to produce matrix B, then the determinant of A is equal to the determinant of B. Okay? Repeating, if a multiple of one row of matrix A is added to another row of matrix A, and this sum produces another matrix, we are calling this matrix B, then the determinant of B is equal to the determinant of A. Property number 2. If one row of A is multiplied by a scalar to produce another matrix, and we are calling it matrix B, then the determinant of B is equal to K times the determinant of A. Okay? Saying it again. If one row of A is multiplied by K, and this multiplication results in another matrix, let's call it matrix B, then the determinant of matrix B is k times the determinant of matrix A. Third property, letter C, if two rows of A are swapped to produce another matrix, and we are calling it matrix B, then the determinant of B is equal to the negative of the determinant of A, okay? Again, if two rows of matrix A are swapped, let's suppose you are putting row 1 in the place of row 4 and row 4 in the place of row 1, then the determinant of the new matrix is the negative of the determinant of the original matrix. Fourth property, letter D, the determinant of the inverse of a matrix is equal to 1 over the determinant of the original matrix. We have a matrix A. The determinant of its inverse is 1 over its own determinant. Let's see an example. Find the determinant of the inverse of A. Let's suppose that A is sin x, and sin x, cosine squared of x, cosine x, 1, 1, 0, 1. We are going to use the rule of Sarri to calculate, and then we put it here, sin x, sin x, sin x, cosine squared of x, cosine x, and 1. Okay? And we're going to use the rule of Sarri to calculate the determinant of matrix A. We are going to use the zeros here as our guide. And as we saw, these products here are multiplied by -1, and the products of the right keep the original sign. In this way, the determinant of A is equal to -1 times this product here, it's sin x cosine x. This here is 0. This here is sin x cosine squared of x plus, now this product here, sin x cosine x. This one here is 0 because we have a 0 here, and this is sin x. If we carry out, okay, I'm gonna let you try. If we carry out, we find that the determinant of matrix A is sin x cubed. And we have now to use this property here, because we don't want the determinant of A. We want the determinant of the inverse of A. Then the determinant of the inverse of A is 1 over sin x cubed, okay? A system of linear equations. A system of linear equations is a collection of two or more linear equations involving the same variables, a solution of the system is a list of numbers that makes each equation a true statement. System of two equations. Finding the solution set of a system of two linear equations can be easily accomplished by graphing. Let's see this example here. Find the solution of the system. We are going to use a graph to understand graphically the solution of the system. Firstly, let's work on this equation here. The first equation, x minus 2y equal to -1. We are going to look for the points of intersection with the x and y axis. Firstly, the point of intersection of the line with the y-axis is zero in x, and a number, we are calling it y1, is the point the line intersects the y-axis. We have only to substitute this point here in the function or in the equation, and then we find that 0 in x minus 2y1 is equal to -1, and this produces y1 equal to a half. This is the first point. Similarly, the point of intersection of the line with the x-axis is x2 and 0. At the point the line intersects the x-axis, the y-coordinate is 0 and the x-coordinate is a number. We are calling it x2. Okay, we simply substitute this in the equation and we find that x2 minus 2 times 0 is equal to -1. And in this way, x2 is equal to -1. And we come here and plot this line here. For the point the line intersects the y-axis, x is 0 and y is a half. And for the point the line intersects the x-axis, the y is 0 and the x is -1. In this way, the line will be okay. This is the graph of this equation here. Let's do the same for the second equation. We are going to work on the second equation. This equation here, -x plus 3y equal to 3. For the point of intersection of the line with the y-axis, we have 0 for x and y1 for y. And we simply substitute this in the equation, and then negative 0 plus 3 times y1 is equal to 3. And in this case, y1 is equal to 1. Subsequently, we look for the point of intersection of the line with the x-axis. It's going to be x2 and 0. We substitute in the equation, and then we find negative x2 plus 3 times 0 equal to 3, and we find that x2 is equal to negative 3. And we plot in a similar way. We plot it. We're going to have here the point of intersection with the y-axis. We have 0 and 1. And the point of intersection with the x-axis, we have negative 3 and 0. We have negative 3 here. And then the line is going to be this. Okay? And the point of intersection is the solution of the system. The solution of the system is the point of intersection of the lines. And this is 3 for x and 2 for y. The solution of the system is the point 3, 2. Okay? And this is all for 2x2 systems. It is simple to see the solution of a 2x2 system because we can put it on the plane, on the xy plane. Now let's extend this to systems of more equations. System consistency. A system of linear equations is said to be consistent if it has either one solution or infinitely many solutions. On the other hand, a system is inconsistent if it has no solution. Solving a system of linear equations. In general terms, the strategy for solving linear systems consists of using a pivot and place zeros below it on every column of the augmented matrix. Let's use this example to understand how we solve a system of linear equations. And to do this, we are going to use the augmented matrix. The augmented matrix of this system here is 1, 0 and 5, negative 2, 2 and 0, 1, negative 8, negative 5, 0, 8 and 10. This is the augmented matrix of the system. The next step is to operate on the rows of the augmented matrix. We are going to use A11 equal to 1 as our pivot and place zeros below it. We already have a 0 here. We need to put a 0 here in the place of 5. Okay? And for this end, we multiply row 1 by negative 5 and sum with row 3 and put in the place of row 3. Okay? Negative 5 times row 1 is, we are going to multiply each of these entries here by negative 5. Negative 5, 10, negative 5, 0, 5, 0, negative 5, and 10. And we simply sum 0, 10, negative 10, and 10. Before substituting, we can reduce it, okay? We can make it simpler by dividing by 10. We are going to divide this by 10, and then we get 0, 1, negative 1, and 1. And we simply substitute this here in row 3. This is what we are going to do. Zero, 1, negative 1, and 1. The next step is to use row 2 and row 3 to put a 0 here, okay? This is what we are going to do. What if we multiply row 3 by negative 2? We are going to do this. 0, negative 2, 2, and negative 2. And we are going to sum with row 2. 0, 2, negative 8, and 8. And if we sum and we find 0, 0, negative 6, and positive 6. We can further reduce it, make it more simple, and divide by negative 1, and we find 0, 0, 1, negative 1. And we are going to substitute it in row 3. 0, 0, 1, negative 1. And the last step will be to divide row 2 by 2. If we divide row 2 by 2, here in the place of 2 I put 1. In the place of 8 I put 4. And in the place of 8 I put 4. Then we have already the system in the echelon form. Okay? It is already in the echelon form. And the echelon form allows us already compute what's going on. For example, here I have that z is equal to negative 1. Okay? We can infer here this. Take a look at this. We have that 0x plus 0y plus 1. Z is equal to negative 1. And knowing this, we can simply understand, is a straightforward conclusion, that z is equal to negative 1. Let's consider this row here. 0x plus y plus minus z is equal to 4. But we already know that z is equal to negative 1. Then y plus negative 4 times negative 1, 4 is equal to 4. We know then that y is equal to 0, okay? 0 plus negative 4 times negative 1 is equal to 4. Then we know that y is equal to 0. Subsequently, we compute the value of x. X minus 2 times y plus z is equal to 0. We already know that y is equal to 0. We don't have to worry with y. X is equal to z. Then we know that x is also equal to negative 1. And we have the solution of the system. X, y, and z, they are equal to negative 1, 0, negative 1. This is the solution of the system, okay? When we reduce the matrix, the augmented matrix to its echelon form, we can immediately find the solution of the system. To finish, let's consider this last example. Using the echelon form of the augmented matrix, state whether the following system has a non-trivial solution. Let's go to the solution. Obviously, x, y, z equal to 0, 0, 0 is a solution to the system. But this is the trivial solution, because if you substitute 0 in x, 0 in y, and 0 in z, of course the result is 0. This is the trivial solution. We are not interested in the trivial solution. We want to state whether the system has a non-trivial solution. And to do this, we will operate on the rows of the augmented matrix. Let me write the augmented matrix. Five, negative 2, 1, negative 4, 4, 8, 0, 0, 0. Okay, this is the augmented matrix. We are going to use A11 equal to 3 as our pivot, and we are going to seek to place zeros below it. Okay? We are going to use these additions. If we use R1 plus R2, if we use R1 plus R2 and substitute in the place of R2, we are going to put a 0 below the pivot, okay? The pivot is entry A11, and this is entry A21. We want to put a 0 here. Observe that 3 plus negative 3 is 0. Okay, so if we carry out this addition, a 0 is going to appear here. Alright, secondly, we do the following. Negative 2 times R1 plus R3 and substitute in R3. Okay? A11 is 3, positive 3. If we multiply it by negative 2, it becomes negative 6. If we sum with the 6, we get a 0. That's why we are going to, but we cannot, okay, this is a property of matrices. We cannot simply multiply entry A11 by -2 and sum with entry A31. No, no. We have to multiply the entire row by the number. Okay? So instead of only multiplying this 3 by -2, we are going to multiply the entire row by -2 and sum with row 3. And then we eliminate the 6 and put a 0 here. After we do this, we find 3, 0, 0, 5, 3, -9, -4, 0, 0, 0, 0, 0. Okay? And now we are going to use this entry here, A22, equal to 3 as a pivot, and eliminate this -9 here. We are going to sum. I'm going to tell you it is going to be 3 times row 2 plus row 3. Observe that 3 times 3 is 9. 9 plus -9 is 0. And then we successfully put a 0 here. But we cannot simply multiply entry A22 by 3. We have to multiply the entire row by 3. Okay? If we only multiply one entry and forget the others, we change the matrix. To not change the matrix, to let the matrix preserve its characteristics, we have to multiply the entire row. Okay? And after we do this, we convert this matrix to this. 3, 0, 0, 5, 3, and 0, and -4, 0, 0. Okay? 0, 0, 0. This is the echelon form of this matrix here. This is the original augmented matrix, and this is the echelon form of this matrix here. And from this, we can infer that three times x plus 5 times y minus 4 times z is equal to 0. We can also state by looking at row 2 that 3 times y is equal to 0. Okay? For 3 times y to be equal to 0, the only possibility is y equal to 0. Y has to be equal to 0. Then the first equation is reduced to, the first equation is reduced to 3 times x minus 4 times z equal to 0, in which x is equal to 4/3 of z. We understand z as a free variable, and the system has infinitely many solutions of the sort. This is the solution of this system here. And we have understood that z is a free variable and x is dependent on z, okay? They are not independent on each other, they are dependent. Z times 4/3, 0 and 1, okay? And the system has infinitely many solutions, every one for each value of z, which is a free variable. Okay, my friends, this is the video that I wanted to make about matrices, determinants, and linear systems. I hope you enjoyed it and learned from it. I am a teacher. If you want to book a lesson with me, use my WhatsApp number, guys. Goodbye!